Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our finite element analysis and design software, RFEM. The topic for today's webinar is design of structural glass systems in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer. We are located in Philadelphia, Pennsylvania. My colleague Uli Lex will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Leipzig, Germany office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the webinar. You can do so within the same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So to quickly explain RFEM, which is our main program, and the add-on module concept with RF glass. So RFEM, as I mentioned, is our main program where we can completely model and load our entire structure. And the modeling would include other materials like steel, concrete, aluminum, timber. We can integrate with BIM software such as Revit, Tekla, AutoCAD. We can fully create our load cases and generate our load combinations, whether that's according to the ASCE 7, the NBC standard, or many other international standards. And finally, we can run a full analysis to get things like deformation, support reactions, internal forces for our members. The add-on module RF glass simply allows us to define our different glass layers. So for laminated glass, insulated glass, we can individually define those layers. We also can account for things like climatic loading, temperature differences, altitude differences. The program will automate that for us within this add-on module. And finally, we can run a stress analysis and see our stress ratio check, as well as serviceability, and view all of those results within the RF glass add-on module. What's nice is that you'll be able to individually see the stresses for each layer, which we'll be taking a look at for examples today. So there are three different types of glass structures. The first is single layer glass. Now, when we are considering the use of our add-on module RF glass, we have two options when it comes to single layer glass. We can run a calculation according to a 2D calculation utilizing plate theory. The second option is a 3D calculation utilizing solids. So this would, instead of using 2D surface elements for plate theory, for solids, we will utilize three-dimensional finite elements. Now, both have their pros and cons. Obviously, a 2D calculation is going to be a little bit quicker, maybe not as detailed of results as you would see with the 3D calculation with solids. The second type of glass is laminated. Now, with laminated, we have two or more glass panes with a foil or resin layer in between. For this option, we also have 2D and 3D calculations available. So the first 2D calculation considers shear coupling according to plate theory. With the shear coupling and the 2D option, we will consider this a rigid shear coupling. And you can see that indicated by this picture here, showing the cross-section of the layers and the rigid coupling at the ends. Now, as far as the 2D calculation without shear coupling, this is still according to plate theory. Well, there will be no relationship in terms of the shear transfer between each of the individual layers, indicated by this second picture here. The third option is with solids. So what's nice about this is that we will actually account for the shear stiffness between those intermittent layers to come up with the exact shear transfer between the shear couplings. The third type of glass structures is insulated glass. So this would include glass panes separated by a primary seal, a secondary seal, a spacer, and then that gas layer. And this is indicated by the picture over here on the right. Now, for this type of glass structure, we will always run a 3D calculation with solid elements according to a large deformation analysis. And for this large deformation analysis, we utilize the Newton-Raphson method. So plate theory is not available here because the gas layer adds too much complexity to these glass surfaces. When we launch RF glass, there are two different calculation types that we need to choose from, either local or global. So our first example today will utilize a global calculation. Now this considers the entire model within RFEM. So things like supports, nodal supports for today, boundary members, those are all taken from what we've modeled in the main program RFEM. Now the analysis options for a global model is 2D only, so we can only run this according to plate theory with a linear analysis. So something like insulated glass would not be available for a global calculation. Now, the other calculation type is local. So this is where we will actually be looking at an individual glass surface only. Things like support types, boundary members, those have to be redefined within RF glass. And this provides us with the opportunity to get a little bit more detailed when it comes to the support types, where they're exactly framing into the surfaces or the solid elements in this case. Now for local, we also have the ability to run either a 2D or 3D, plate theory or solid. And so that further allows us to run a linear or large deflection analysis. So this will be our second example today, utilizing the local calculation. I did want to touch upon the NCSEA putting together a new design guide, and this design guide was just released this year, and it's called Engineering Structural Glass Design Guide. And to phrase it exactly how they phrase it within the design guide itself, it's to collate relevant design references, requirements, and analysis methods into a single source for easy reference. I believe that when it comes to glass design within the US, it's a little bit difficult because unless you're an expert, there's really no clear-cut design path to take with glass. So what the NCSEA took upon themselves is to compile this document, and it's not very long, to kind of compile maybe some theoretical literature along with what we do know within the US, maybe according to the ASTM design guides, as well as Eurocode references, so that engineers with not a lot of experience can relate to this design reference. So I did want to touch on Chapter 6 with finite element analysis. This design guide goes to state that, of course, we can always run hand calculations for glass design. But at some point, these models may get a little bit too complex, so that's when we should turn to a finite element analysis software. They also refer to global and local, but this is a little bit different terminology than what I just discussed with our global versus local. With the global model within this design guide, they state that the glass elements can be simplified into 1D member elements. Now, this might be most beneficial just to gather internal forces, the load path, things like reactions, and to run a simple linear static analysis. Now, by all means, this is possible within RFEM as well. The other option when we need to get a little bit more complex is to run a local model. Now, local models in the design guide, they reference 2D and 3D elements. So this is what we're doing with RF glass, with surface elements and solid elements. Now, this is more applicable for getting behavior on plate bending, things like shear transfer, which we just touched on. As far as material nonlinearity, the design guide states that glass is a linear material model. Well, we also consider it an isotropic linear elastic material, but that nonlinear connection should be considered. Now, this might be more relevant for something like point-supported glass. We can also take into consideration these nonlinear connections with things like contact solids, and we don't have time to focus on something like point-supported glass connections today, but I do plan to do a follow-up webinar sometime within the coming months to maybe more focus on this. Now, as far as geometric nonlinearities, the design guide states that effects like P delta, large deflection theory, should be considered for maybe buckling checks or weak axis bending, where small deflection theory loses its validity. Well, in our program, utilizing RF glass according to a large deflection theory with solid elements, we would cover P delta as well as large deflection theory as well. So that is also possible. Okay, so we are finally ready to jump into our first example. So it's quite common with glass design that we want to integrate it with our own custom extruded sections. These aren't sections that you would find within the AISC or the ADM, but rather there's some type of unique cross-section. Well, within RFEM, you most likely won't have access to quickly define this cross-section without having to manually calculate all the cross-section properties. So we've created a program called ShapeFin. Now, for those of you who are familiar with RFEM, the interface looks almost identical. So that's nice that there's that familiarity. What we're going to do today, you can import in an AutoCAD file, but today I'm just going to draw my cross-section, and I'm going to have the program calculate the cross-section properties that I can later bring into RFEM. So what we'll start off with is a new polyline. And with this polyline, I need to define the thickness of my cross section. So we'll set this to something fairly thin at 0.15 inches. Now, as I draw this polyline, I can also take into consideration a bend radius. And so you can set that bend radius here. We'll choose 0.04. The material must also be specified. Steel A992 is probably default when you first launch the program. And we can just enter into our material database here and use our filters over on the left. So instead of steel, maybe we drop down to aluminum and we take a look at ASTM and further filter to the ADM 2015. Now you can see the long list here of all of the aluminum materials. So most likely you'll find what you need. And today we'll just take a look at the T6510 for extrusions, and here are all of my material properties. And I can click OK through these dialog boxes. So now I am taking a look at my graphical interface here, and I can begin drawing my cross section. So all I'm doing is snapping to a few various points here on my drawing grid, and you'll notice that that bend radius is taken into consideration when I turn these corners. Now I'm only going to draw half of the cross section because what I can utilize are some of these AutoCAD type features that make our lives a little bit more efficient. So I can select the left side here of my cross section and use my mirror tool. So up here in the tools is the mirror option where I can create a copy and mirror about the origin. I click OK, and just like that, fairly simple but custom extruded section is created. So I'm almost ready to run the analysis to get my cross-section properties, but I want to jump to materials. For aluminum, you'll notice that the yield strength is automatically set to 0 here. So if I try and solve this, I'll get an error. The reason why, if we take a look at the aluminum material, is that there are different yield and ultimate strengths depending on if we're looking at tension, compression, shear. So the program simply doesn't know what to use when calculating the plastic cross-section properties. So I can realistically set this to whatever, it doesn't matter, 35 and 40. The reason why is because I'm going to redefine the material once I get into RFEM. So for now, just as a placeholder, so to speak, we can now run the calculation with that applicable yield strength set in there. So in just a second, you can see it solves pretty quick, and now available in my results table are all of the cross-section properties for this custom cross-section. So we want to save the results, and you have to save the results with these calculated cross-sections in order to integrate it in with RFEM. So now changing programs here, we'll go over to the program RFEM. To begin with, I need to create a model name. For this one, we can call it webinar. Now, the type of model is 3D. The load combinations, this is where we can set the automatic load combination generator according to the ASCE 7 2016. We have the NBC 2015, as well as many other international standards. They're also the older standards if we hit this button here. So when this checkbox is checked, it will automatically create those load combinations. When I uncheck this, that allows me to just manually define load combinations. For today, we'll go ahead and utilize the program generating these for us. I click OK, and then up pops my new file. So here's my graphical interface that we'll utilize to begin modeling our facade wall today. We also have our tables down here at the bottom to work with. You can import and export directly to and from Microsoft Excel. We'll certainly be utilizing these quick tools up at the top. And over on the left is our project navigator, maybe a little bit more unique to our program RFEM. Well, as we begin to model here, all of our input data will be available in these tree type lists. The results will also be available here. So what I'm going to do is I'm going to change around my drawing grid to begin drawing my facade wall. So I want to start off with a new member. And so I click on my new member tool. And the member type is set to beam, and I'd like to take a look at my cross-section library. Well, here are all of my cross-sections available. Now, this would include shapes from the AISC, from the CSA, from the ADM. You also have these parametric thin-walled sections here, but you'll notice that I don't see that custom section that I just created. It's not an option to choose from. So that's why we're choosing this option down here to import the cross-section from shape thin. Then I just simply navigate to where I saved that file, and there's my custom cross-section available to me. So once I load this, I can also modify the material here. So perhaps this was set to steel A992 or whatever default material was in the program. Well, we can quickly access our material database here. Again, this looks familiar. This looks like exactly what we saw in shape thin. We can filter on the left to the ADM 2015 to choose our T6510 for extrusions. And I click OK. So just like that, we now have this custom cross-section available to us within our main program, RFEM. So all that I'm doing here are just snapping to a couple points to create my boundary members for my first glass panel. So once I'm done with that, I've created these 4 members. I want to draw in my glass panel. Well, we can do this with a new surface element. So up in my quick tools, just like how I drew the beam member, we can draw a surface element. And you'll see here we have multiple surface shapes, but for today, we're just going to utilize a typical rectangle shape. Now this is where we choose the stiffness from our drop-down menu set to glass. As far as the material and thickness, this doesn't matter. We're going to override this in just a little bit of time with the RF glass add-on module. So aluminum, steel, concrete doesn't matter. Thickness doesn't matter. That's just another placeholder. So what we can do is just snap from one corner to the other, and then that 2D surface is drawn for us. So let's also say that we would like to release the moment of this glass panel framing into these boundary members. Maybe it's not a typical connection type to transfer the moment from this surface element to those boundary members and vice versa. So how do we do this? Well, under Insert and Model Data, we have the option for what's called line hinges. And I can assign 2 lines graphically, and up pops my dialog box. So right now, I don't have a line hinge definition. It just says none. So what I'd like to do is to create a new one. So here are my 6 degrees of freedom for my local axes according to my line. Now this is not the local axes of my surface. It's not the local axes of that beam, but it's actually the shared line that they have in common. So what I want to do here is to release the moment about the local x-axis of the line, which is along the line length, and I click OK. So now I can select this surface and then easily click on the 4 line elements on the boundaries, click OK, and now we can see the line hinge shown here with this available symbol. I am going to select everything here, just like what I would do in AutoCAD, for example, and use my Move Copy tool. I'm going to create 5 copies in the displacement vector of 3 feet in the global X direction. I click OK, and now it copied over the line hinges, the boundary members, and these surfaces. Well, I've decided that for this 3rd panel and this 5th panel, if I hold down my Control key, highlight them, and I hit Delete on my keyboard, I want to subdivide these into smaller glass panels. Well, for this, I want to draw a new member again. Now, my shape thin section, along with my material, aluminum, has already been set. I don't need to redefine that. So I'm utilizing the same shape and the same material. All I need to do is to click OK, and then I can begin modeling here to create some smaller glass panels. And we'll go do the same over here, but we'll just subdivide this one in half, and I can right click. Now I'm going to utilize this tool up here to connect all of my lines, and that just creates a node here and separates these members. Now you'll notice that I obviously lost my glass surfaces, so we want to go back to draw a new rectangular surface, set the stiffness to glass. Remember, the material and thickness don't matter at this point. We're just really defining the geometry at this point. So snapping from one corner to the other, I can quickly take into consideration these smaller glass elements. Now I've also lost my line hinges. So under Insert, Model Data, Line Hinges, assigned to lines graphically. We've already defined the type. I don't need to redefine that. All I want to do now is to select this glass panel and select the 4 boundary members. And I need to do the same thing for all of these new glass surfaces. So you can see the benefit here of utilizing that Move Copy tool so that we don't need to individually apply these line hinges to each surface like we're doing now for these smaller segments. So we'll go ahead and do the same thing for the 5th panel point location, and finally for our smaller panel here, we are done. Okay, so the geometry is pretty much accounted for, but there's one thing I'd like to adjust. If we take a look at this member here and I choose a visibility by selected objects and I zoom in here, well, number one, you'll notice I get a great rendered shape here of my cross section from shaped in. Although it's custom and we might have some different lips and extrusions and whatever else, you'll always get a nice rendered view, so I know exactly where the orientation of my members are. Well, for these internal members, I actually want to rotate them 90 degrees. Maybe that's just the type of connection for this facade wall. So canceling out this visibility and rotating this around, let's turn this into wireframe view, and I'm going to select all of my internal members here. So I didn't select the outside boundary members, I just simply double click on one of the members, and then right away I can adjust the angle to 90 degrees and I click OK. So now when I turn back on the rendered view, all of these internal members are now facing towards the global y-axis. So we would like to support this wall. How we'll do so is with nodal supports. And again, it's just a simple tool up here, a new nodal support. Now we have a couple default options here, hinge, which is a typical pin nodal support, and rigid, which is fully fixed nodal support. So for the bottom of the wall, let's just utilize a simple pinned application. I click OK. I just highlight along the bottom of my wall here, and I lost it, so 1 second. I highlight the bottom of my wall, and now that pin support will be applied to every node along the bottom. As for the top, I also want to apply a nodal support, but for this time, I don't want to use one of these default options. I'm going to create my own nodal support. Well, here are my 6 degrees of freedom, 3 degrees in translation, 3 degrees in rotation. I'm going to release translation in the Z direction. So I want this wall to have a roller type support in the vertical direction. And I click OK. So now I have this user-defined type of support. I click OK, and I can highlight the top of my wall here. So realistically, the modeling of the wall itself is complete. So we want to move on to applying a couple loads to this wall. For this, we need to first define our load cases. So another button up here in our toolbar called New Load Case. And up pops my Edit Load Cases and Combinations. The first load case is going to be dead load. Now the action category is important because this tells the program what load factors should I apply according to the ASCE 7. So this one will be according to the dead load, and self-weight is automatically activated here. For my second load case, we will call this one wind. The action category will be set to wind. Self-weight is not activated here because we don't want to account for it twice. The combination expressions tab. This is the program telling me, okay, I'm going to generate all the LRFD load combinations, which we can see here, and I'm going to generate all of the ASD load combinations. Now, to see these individually listed out, let's go to the load combinations tab, and here are my 3 LRFD load combinations and my 3 ASD load combinations. Now, this is a fairly short list because we only have 2 different load cases defined. So once I'm done setting up my load cases and load combinations, I need to actually apply a load to this wall. So to apply a load, you want to make sure, and by the way, we can see now these load cases and load combinations generated for us here. Let's make sure we're in the LC1 dead load. So for dead load, I'm going to make the assumption that I only want to apply self-weight here. Well, remember that's already accounted for within the load case itself, so I don't need to do anything further. As for wind load, I scroll to wind load, and I do want some type of surface wind load acting on the face of this wall. So what I'm going to do is I'm going to go to a new surface load. Here, I'm going to apply a force, and the load direction is going to be in the global Y direction. So you can see here my global axes, and I want this load acting on the face of this wall. The load distribution is going to vary in the vertical direction. And what do I mean by that? Well, at the top of the wall, I would like the magnitude to be something around 25 PSF. But at the bottom, let's decrease that slightly to around 20 PSF. The thing that I do need to define is to tell the program, well, what's the top of the wall? What's the bottom of the wall? How do I want to vary this? And that's easy enough to do by just choosing any arbitrary point first at the top of the wall and a second point at the bottom of the wall. And now the program knows what magnitudes to associate at which points. I click OK. And then I just simply highlight my entire wall. And just like that, we have our wind load applied to the surface here, which is varying in the Z direction. So pretty simple for our loads being applied today. We can see the load combinations here with the load factors applied for dead load and wind load and so on. So one final thing to do before we jump to the RF glass add-on module, and that's to take a look at our finite element mesh. Well, these are surface elements, so we want to obviously take a look at the FE mesh settings to make sure that we're going to get accurate results. Under Calculate FE mesh settings, the global FE mesh length is always set to 1 foot for a new file or a new model within RFEM. Well, let's leave it as the default, and here I'm going to regenerate the FE mesh once I click OK. And I can see here that my FE mesh is a little bit too large. I only have 3 FE mesh points along the width of these glass panels. This really just isn't ideal to give us accurate results. So it's always suggested that we need to go smaller than this. Now this will increase our solution time slightly, but in turn, of course, we need to see accurate results. So under Calculate FE mesh settings, let's try something like 0.25 feet, and we can regenerate this again. Well, this looks much better, and I know that's a little difficult to see, but maybe we turn this into wireframe view. We can see the FE mesh settings along the width is much smaller, so that looks much better. Okay, so the geometry, the loading, the FE mesh, everything's done, but remember we still have these aluminum surfaces here. So this is where I want to launch the add-on module RF glass. Everything you've seen up until now was in our main program, RFEM. So in our project navigator, well, here is our long list of add-on modules. As you can see, RF glass is one of them. So we can launch this add-on module and up pops nothing more than a dialog box. Now, as I mentioned within the PowerPoint, we need to first choose the calculation type. And for this, our first example, we're going to utilize the global calculation. The standard is set to none because we're just doing a stress analysis and design. These surfaces that we're designing for, well, you can see they're all highlighted here because they're all being selected for design, but by all means, you don't need to choose every surface if you're not interested in it. For the ultimate limit state design, we'll choose our 3 LRFD load combinations, and our serviceability, we're choosing our 3 ASD load combinations. As I mentioned, we can also check deflections. Then it's as simple as just working down this list from top to bottom. So we move on to the layers. So this is where we define our different glass layers. The first thing to do is to select the surfaces that this first composition will apply to. So I can highlight them all, and you can also create more than one composition. So maybe these smaller panels, I wanted to use a thinner glass. Well, you could certainly do so all within the same model by assigning different surfaces to different compositions. So we're going to utilize laminated glass. The first layer type is going to be glass. And here is where we would access our material library. So typically when you launch this for the first time, you're really only going to see a very small amount of materials that really aren't relevant for the ASTM or the US market. So this is why we give you the opportunity to define your own. And for me, I've created a thermally toughened float glass, and I have placed it in what I call an ASTM glass standard. So depending on the manufacturer, or if you're going off of the ASTM standards, you would just simply add that material here with this option to create a new material, put in your material properties, and that will always be available for all file types when you're modeling in RFEM. So the first glass layer will have a thickness of 0.12 inches. The additional information here is just based on the material, so we probably won't be making any adjustments to that since that's defined directly by the material itself. The second layer is foil. So when we go to the material library for glass and foil, we can see here that we have some options that are not related to any standard, like PVB would be a common inner layer, for example. We do have a manufacturer here for Century glass according to the ASTM. And by all means, again, you can always add your own inner layers as well, whether that's a foil, a resin, PVB, and so on. So for today, we're going to utilize Century glass at 20 degrees Celsius. I click OK. The thickness is much smaller at 0.01 inches. The final layer for our laminated glass panel is going to be glass. The program makes the assumption you want to use the same thickness. That's fine. So you'll notice here is a graphical representation of my layers, and here is a note showing you what the local z-axis direction is according to these surfaces. So it's very important that you pay attention to the orientation of your local axes of your surfaces to make sure you've defined your layers correctly. Now in this case it's completely symmetrical, so it's not so important, but in our next example we'll see where it does become a little bit more important. You can save these compositions, by the way, and pull them up for any future models as well into a library. So what's happening behind the scenes? Well, for each individual layer, I can take a look at here the stiffness matrix for that single layer. Now, what the program is doing in this module is it's taking into consideration all of these layers that I've just defined, and it's creating a global stiffness matrix, and we can actually view that here within this add-on module. This global stiffness matrix is then exported back out to RFEM, and we're going to rerun the analysis here with the correct materials stiffness matrix to ultimately get our results back into this module. So that's kind of what's going on behind the scenes. Now, one last thing to look at here is edit composition details. Well, the only details that we really have here, not too much. We can either consider coupling, and remember, according to 2D plate theory back from the PowerPoint, when we consider coupling, it's a fully rigid shear coupling. When I uncheck this, then we don't have any shear coupling between any of the layers at all. So for today, we'll keep this as a rigid shear coupling. And finally, we jump down to serviceability data. Well, we can also design the serviceability checks here. So we can select all surfaces that we're interested in for the deflection. The reference length, well, this is the length that's going to be used in our limiting deflection ratios. The program has a few defaults here, the minimum boundary line, the maximum boundary line, or you can type in your own length definition. So for today, maybe I use the maximum boundary line of 10 feet, which is the total height of the wall. Is the deformation related to the undeformed system? Is it a displaced parallel surface? So basically, is this absolute or relative that we're supposed to be measuring these deflections from? Well, today we'll keep this according to the undeformed system, and that's what these pictures show down here to clarify exactly where the deflections will be measured from. You can also set if this is a cantilever surface as well. So the question is, well, we've defined all this information, but what's my limiting deflection ratio? That's controlled under the standard button. And we can see here for this first line here, because we only have characteristic load combinations for ASD back on the general data tab. The deflection limit by default is set to L over 100 for simply supported, L over 50 for cantilevers. Glass is obviously a little bit more sensitive to deflection than what we'd see with a steel beam, which might be more like L over 300. So by all means, though, you as the user can control what these limiting deflection limits are. And just like that, we're finally ready to run our calculation. Now, this takes a split second, and that's because it's a linear static analysis. We're just exporting out that global stiffness matrix, and then we're bringing back in the results into RF glass. So once it's done with the calculation, our results are presented to us in this table format. We can view the max stress ratio by loading. We can view the max stress ratio by surface, so we should have all of our surfaces shown here. We can view the max stress ratio by composition. So when we're looking at this table, and this is the max stress ratio by surface, you'll notice that as I'm scrolling here through my table to different values, the program is highlighting in the background exactly which surface I'm looking at. From there, we can take a look at our normal stresses with in the local XY axis, our shear stresses, our normal principal stresses as well. And ultimately, we're seeing the required stresses based on the analysis, as well as our limiting stresses, which is just based off of our materials, and finally, a ratio check for our stress design. The program gives you the summary here. So out of all these surfaces, the max ratio is 0.31, so relatively low. And we have our nice green smiley face here because he's less than 1.0. If you're seeing a red sad face there, then you know that you probably are a little overstressed and you're over 1.0. The max displacements, this is our serviceability check. So we can see the displacements based on the analysis. We see our limiting displacements based on that L over 100 ratio. And then we have a serviceability ratio given to us, with the controlling one being 0.61 along with our green smiley face. So remember, for any of these tables, you can export directly to Microsoft Excel for further sorting. So obviously Microsoft Excel is going to have much more capabilities when it comes to that. The parts list is also given here, which is a material takeoff. So we will also give you that information. Now, the tables are nice, but it's also beneficial to jump to our graphics view. So with our graphics view, we are technically still within this add-on module. You can see it here from our drop-down RF glass, but we're viewing all of our results graphically back within RFEM. And now our results tables are presented to us here under the Project Navigator. We see our loading combinations. From here, we can view the two different glass layers. Remember, we have one on the inside and one on the outside. And even furthermore, you can view the top, the middle, or the bottom stresses for each layer. From here, the stresses are given to you that you can scroll through, whether that's shear stresses. Maybe you want to take a look at ratios here for, however the stress checks come out. And that's all available to add to your printout reports. Maybe you want to make section cuts through this, so everything is possible here graphically. So that really sums up a global calculation type within RF glass. So let's say that we ultimately decide we want this to be insulated glass instead. Well, remember, for insulated glass, we have to run a local calculation. And a local calculation, well, we can only really consider one glass element at a time. So we're going to take one of these panels, and what I did under a different file here is I've just simplified it. So I just took one of those glass panels, kept the supports, kept the boundary members. I even kept these same wind loads the same. And for the second example today, utilizing insulated glass, we want to launch RF glass again. Now, when we launch this add-on module, the calculation type here will now be set to local. The standard is still set to none. The surfaces that I want to design, well, we only have one surface here, so let's move forward with this one. As far as the load combinations, I'm actually going to come back to this. Right now, I'm just going to put a simple placeholder in for my LRFD design. And the reason why is we're going to make some adjustments here with climatic loads later on. So in just a minute, we'll get back to this. In the meantime, we simply move up or down our list over here. And you'll notice a few more tables are available now. So the first thing for our layers, and this should look familiar, we want to select our surface here, surface number 3. The layer type is going to be glass, and I still have my thermally toughened float glass from the ASTM with a thickness of 0.22. The next layer is going to be gas, and this is where we can utilize our material library here. We have a few gases implemented. Again, you can always add your own gas. For today, we're going to utilize argon with the gas properties given here. The third layer is going to be glass as well at 0.22 inches. The fourth layer is going to be my foil. And again, I'm going to go back to my material library here, and I'm going to choose that Sentry glass for 20 degrees Celsius. I click OK. The thickness is 0.01 inches, and my final fifth layer is going to be glass again at 0.22 inches. So there are my 5 layers. Now you can see again the profile here of our different layers, and this is why it's incredibly important to pay careful attention to your local z-axis. Even more so with insulated glass, the program has to determine what's the external side and what's the internal side. So if these don't match up to what you'd like to see, in our case, we want the gas closest to the external side, then you need to make some adjustments here with your layers to make sure that those match up. Let's take a look at the composition details. So this is quite a bit more information than what we saw with our last example. Remember, we only had shear coupling to consider here. Well, now you can see the method of analysis is automatically set to a large deformation analysis. And this is because we have introduced a gas layer into these glass surfaces. And we run this according to a Newton-Raphson. The modeling of the laminated glass. So this is interesting here. This will also be a 3D calculation utilizing solid elements. So by the way, in the background, once we run an analysis, that 3D model is going to be created with solid elements instead of surface elements. So what we can do here to consider coupling, we also have to utilize 3D elements for the laminated portion of our glass. But if I uncheck the coupling, then it will automatically use plate theory for the laminated portion of my glass here. Today, we're going to consider coupling and just utilize solid elements throughout the entire surface of this glass panel. Save created temporary models. So I just mentioned that in the background, the program is going to regenerate this entire RFEM model. And instead of 2D surface elements, it's going to create 3D solid elements. And that's all going to go on behind the scenes, but you do have the ability to save that created temporary model and to actually pull it up like you would any other RFEM model. And I'll actually check this here and I'll show you what one of those looks like. Then we just have some further FE mesh refinements here, and we can click OK. So line supports and nodal supports. You remember from the PowerPoint, I said that you have to redefine your support types with a local calculation. Now the program does, so technically these support types shown in RFEM now will be completely ignored. That's why we need to redefine it here. But the program is smart enough to make an attempt at defining what you already have drawn in the RFEM model. So as you can see here, my 2 support types are shown, and the program has some support type defaults here. Now, these support type defaults, if you want to find out more information, number one, you can click on any of them and you can see our 6 degrees of freedom here and how exactly the program is supporting each glass layer. Remember, we have 3 glass layers for this insulated panel, so the program will support as such. Now, if you want any more information, our help file under this little question mark here in the corner really explains a little bit more clearly what's going on. Now, in our case today, I don't really like what the program is suggesting. So instead, I'm going to take this and I'm going to individually define my support types. So the first one will be node number 4, which is my lower node here. And instead of hinge type 3, I'm going to choose user defined. So now when I scroll in here, we can see our different glass layers along with our gas right here, but I can only support the glass. So for my middle layer of glass, I'm going to set this to none. I'm only going to support layer number 1 and layer number 5 at the center line, and I'm going to apply a basic pin support at these locations. Now, let's go ahead and graphically select a couple different nodes here. So we're going to select the upper 2 nodes, and this will also be user defined. I'm going to not support the center layer, and as far as layer number 1 and layer number 5, I'm going to release the X and the Z here. So now we have some type of roller support, and I can zoom up here to see these nodal supports being applied up here to the top. So they're a little large, but essentially you get the picture. It's being applied to those different glass layers. And finally, we have one more node to define, and that's in the lower right corner. I click OK. Again, we can zoom out here to view that in the smaller picture. And we can zoom in. Now for this same concept, we're going to go to user defined. We're not going to support the center layer. The 2 outer layers remains a pin support, but I want to have sliding in the X direction. So now I have manually defined these support conditions. So you can see a huge difference here of utilizing those 3D solid elements and how much more detailed you can get with your support types. Now, the boundary members, same concept as our support conditions. If I zoom in here, well, here is my custom cross-section from shape thin. But I need to tell the program where exactly to apply these boundary members. How do they frame into these glass panels? Well, again, the program makes some suggestions here. They say, you know, the program notices, hey, I see boundary members in RFEM. Let me go ahead and attempt to put them into this glass module as well. Well, this is where you can see we have glass layers 1, 3, and 5 that we can apply it to, and even more so, you can apply it to the upper edge, the center line, or the lower edge. For this case, we will just keep the program suggestions for the boundary members. Climatic load parameters. So this is where we want to take into consideration differences in temperature loads, atmospheric pressure differences, altitude differences. And the reason why is because maybe this glass is being manufactured at a different location than where it's actually being installed. So with this, the program will automatically calculate and figure out what all these gas pressures should be based on this criteria. So you can see here that we have climatic load for summer and climatic load for winter. So the other thing to notice is that we want to keep this checkbox checked. The automatic gas temperature calculation, you can take a look at this. This is pretty advanced. So unless you're a glass design expert, you probably won't be doing much with these options. So we'll leave this unchecked for now. I also do have a document if anyone would like to see it on how these gas pressures are essentially calculated within the program. So feel free to email us after the webinar and I can go ahead and send that back to you. So not to get too complicated within here, the first thing that we need to do is just to put in some information. Number one, where is this glass panel going to be manufactured and what is that atmospheric pressure? Well, let's assume it's somewhere at sea level where the atmospheric pressure is around 14.7 psi. The altitude is 0 feet and the average temperature during the summer is fairly cool at 65 degrees. Now we take a look at where the actual panel will be mounted. Let's assume it's going to be mounted somewhere much higher at 4,000 feet altitude, maybe where the atmospheric pressure is around 10.7 psi. The altitude is set at 4,000 here. Now the average temperature during the summer on the external side of the glass panel is fairly hot at 90 degrees. The gas then can get up to 102 degrees, let's say during the summer, and the internal side is set at approximately 70 degrees Fahrenheit. So the program will automatically calculate these gas pressures for us, but the thing is that we need to put these into load cases so that the program can generate those load combinations for us. Well, if I use my drop-down box here, I only see dead and wind load. So this is where we would actually want to create a new load case. Now this load case looks familiar. This is what we saw before with RFEM. The first load case description is going to be temperature. The action category, we can set this to the self-straining force here, and we click OK. For atmospheric pressure differences, let's once again create a new load case, and we'll call this one Atmos for atmosphere. And finally, one more case here. We'll call this one ALT for altitude. Again, action category set to T. So climatic load for winter now, I think we understand the idea. For the sake of time, I'm not going to fill out all of these, but we'd want to give it the same information for winter conditions. Now, the load cases for climatic loads, what we can do is still utilize these same load cases that I created for summer. And that's because the program is smart enough to recognize that, hey, the gas pressure that's happening during the summer isn't going to occur with the winter. Those won't occur at the same time. So what it's going to do is to create two separate load combinations, one for summer and one for winter. So that's why we can utilize these same load cases. So remember, I said way back when on the very first tab that we needed to get back to this. Well, now I see those additional load cases here, but I don't see my load combinations generated. And that's because RFEM is the program that controls the generation of load combinations, not RF Glass. So what we want to do is to quickly go back to RFEM, and all I need to do is to utilize this drop down. The program automatically updates, and now here are all of my load combinations with those new temperature, altitude, and atmospheric pressure loads. So you can see a much longer list now. Now when I go back into RF Glass, those are all available here for design. So you can move all of the LRFD load combinations here and serviceability. If you'd like to consider all of them as well for deflection checks, you can move all of them over here as well. So that's how the climatic load cases kind of come into play and why we need to update those after the fact. Insulating glass unit. So this is in regards to our secondary seal. Remember, we have an insulated glass, so we need to somehow seal in this gas layer. Well, for this, I'm going to jump back to the PowerPoint to quickly explain what's going on. So with the secondary seal, if I were to uncheck this option, remember this entire section is grayed out. So what's going on behind the scenes, we're going to apply what's called helper supports. Helper supports prevent pressure on the side surfaces. So what do I mean by that? Well, let's refer to this figure down here. We have our gas layer, and our gas layer on either side has glass layers. Now, glass is relatively stiff, somewhere around 10,000 KSI. And the program will automatically model a soft material at the edges, something more around 1.5 KSI. Well, when we apply these gas pressures, remember from temperature, altitude, or atmosphere, without those helper supports, we're going to get side deflection shown at this. So obviously this is not desired. We want to see the deflection within the glass itself, not with the soft material on the outside. So that's why we apply helper supports, which are fairly high in stiffness, so that we'll see deflection more like this with our glass panels. Now, when we choose the option with secondary seal, so we turn this on, we give you the opportunity to define the stiffness of the secondary seal as well as the spacer so that you can accurately consider what that stiffness should be. That's why we now give you the option to turn on or off those helper supports. So if you'd like to define the stiffness exactly, then by all means turn off the helper support and you'll get the exact behavior there. For us, we're going to turn this off today, and we're just going to use those helper supports. Now, number of finite element layers in the gas layers, this is by default set to 2. So this is according to the depth of that gas layer. You can increase that. Of course, the more you increase it, the longer your solution time. But if you have a fairly thick gas layer, then you may need more than 2. The force load distribution. Well, here are my 5 load cases: dead, wind, temperature, atmosphere, altitude. And the program needs you to define at what percentage is applied to the external part of the glass and what is applied to the internal. Well, for this with dead load, it really doesn't matter because we only have self-weight defined. But maybe if we had some other dead load applied to it, such as a line load on top, you'd want to apply 50% to the external, 50% to the internal. As far as the wind load, we want 100% acting on the external. So it's an outside load acting on the face of the surface, so let's keep 100% there. Now, as for temperature loads, really this is kind of up to you as the engineer. Maybe you want 50% on the external, 50% on the internal. Same goes for the atmospheric pressure, and finally, the altitude as well. We just put 50 and 50 for all of those. Lastly, serviceability data. We actually don't need to go through this in detail again because it's exactly the same thing that we saw before. We're going to choose our maximum boundary line of 10 feet. We're still comparing to that L/100 deflection ratio, and the deflection is based on the undeformed system. So now we're finally ready to run our calculation. And as you can imagine, we now have a lot of load combinations to solve for, not to mention the program behind the scenes is creating these 3D models, generating the gas pressure. So it takes a little while to solve. So instead, I'm going to jump to an already solved model here. And essentially, this is what would be presented to us within the glass module. This looks pretty familiar. We'd see max stress ratio by loading, by surface, by composition. So as we can see here, we only have one surface. And we can take a look at, again, our normal stresses, our shear stresses, and ultimately we're going to get a controlling ratio here for our stress design. For this one, relatively low, 0.19. Again, we can check displacements. The controlling ratio here for a serviceability check is 0.43. And a new table would be gas pressure. So again, as I mentioned, the program is smart enough to determine that there needs to be 2 separate load combinations, one for summer. So here's load combination 2, and here's load combination 2 for winter. Same thing for load combination 3, you see summer and winter. So these are the different gas pressures you're going to see based on summer versus winter. Now, of course, it's always beneficial to jump to the graphics, and here is my very, very long list of load combinations. Now, this was an exhaustive list. Maybe for your design purposes, you don't need to consider all of these different scenarios, but it is possible if you'd like to. So basically from here, we're just choosing, a single load combination to view graphically, and just like what we saw with our global example previously, we choose one of the glass layers. So this time we have 3 glass layers, layer number 1, 3, and 5. Then we can view the stresses for all of these different layers and all of these different load combinations. So really, that's what I wanted to show you with the results of this local model. But there was one other thing that I mentioned. I told you that we were going to save these generated models that the program's creating behind the scenes for our solid elements. So I went ahead and this is the model that I have saved in my folder, and the program will automatically generate 3 additional models. You can see it here, RF glass summer, RF glass winter, and then we have one with RF glass without those climatic loadings according to temperature. So for this, if I open up one of those, this is what you're going to be seeing. The program automatically generated your exact same model behind the scenes, and you can pull it open here just like what you would with any other RFEM model. So maybe jumping to the display type here, let me turn off the display of my members. Maybe I turn off the display of my nodal supports, and let's zoom in here. So now you can see instead of a 2D surface, the program is automatically creating these solid elements to represent each layer. You know, here's my gas layer, here's my glass layer in the front, here's my laminated glass in the rear. So the other thing you'll notice too, these are my helper supports. Those are those rigid connections that the program's placing at the edges to make sure that we get desired deflection. Again, the boundary members are shown here. Here's my custom shape thin section shown, and as well as the nodal supports. So those nodal supports are defined on the individual layers that I applied it to. So this is what's going on behind the scenes. And even further, you can take a look at the applied loads. We have the temperature loads, the atmospheric pressure shown here. So again, I've applied 50% to the external, 50% to the internal. You know, you can vary this how you see fit, but this is what the program's coming up for those gas pressures applied to the surface, applied to the solid elements based on those calculations. Same thing with altitude as well. So kind of interesting to seeing what's going on behind the scenes with a local calculation. Okay, so now back to the PowerPoint to conclude this webinar. I know that was quite a bit of information. As always, I want to refer you to our website where we will give you much more information on RFEM, our main program, the add-on module RF glass you saw today, as well as all of our other material capabilities. And our website is Dlubal.com. I also want to encourage you to follow us on our social media sites. One really important one would be our YouTube channel, where we put a recording of webinars just like these on YouTube, and you can watch them at your own convenience. Knowledge-based articles is something that's on our website for tips and tricks and commonly asked questions. Now, our email at our Philadelphia office is info-us@dlubal.com, and our phone number here is 267-702-2815. If you have any questions about the program, today's presentation, or anything else, feel free to get in touch with us. We will have many more upcoming webinars. As a lot of you know, I try and do one around once a month. You can register on our website at Dlubal.com under support and learning and webinars. I also send out a couple of reminder emails when those webinars will take place, which is how probably most of you registered for today's webinar. Many of you are wanting PDH credit for today, and that is great, no problem. I just have a couple of requests. Number one is that you are present for the full hour-long presentation. And number two, if you can send us an email to info-us@dlubal.com, that's info-us@dlubal.com. Just let me know who was in attendance for the webinar at your location, and I will go ahead and issue that certificate for you and email it back to you. So we do request that you send in a request for that. And with that said, I want to thank everyone for attending today's presentation. And as always, we hope to see you at the next one. Thank you.